Stricker, and I'm going to talk to you guys today about acids and bases. We're going to start off with the simple definition, and the simple definition of Arrhenius acid is a substance that contains hydrogen, and that substance will ionize, which means break apart into ions to produce hydrogen ions. Okay, and so that is what an acid is. So an Arrhenius acid must contain hydrogen, like HCl is hydrochloric acid, and that is an Arrhenius acid. And when it ionizes, which means breaks apart into ions, it's going to produce H plus ions and Cl minus ions. Now, an Arrhenius base is a substance that contains hydroxide ions and associates to produce OH ions in solution, which is a hydroxide ion. So if I have sodium hydroxide, that is an Arrhenius base because it contains OH, and it breaks apart into sodium positive +1 and hydroxide -1, which is a hydroxide ion. Now, the next definition of an acid and a base is called a Bronsted-Lowry acid and a Bronsted-Lowry base. This is a much more broad definition. So it's kind of like a square is a rectangle, but a rectangle is not a square. That's kind of how this is. Things that are Bronsted-Lowry acids may not be Arrhenius acids, and things that are Bronsted-Lowry bases may or may not be Arrhenius bases. So, a Bronsted-Lowry acid is called a proton donor. Now, when you think of the word proton, you need to think of H+, because that's what a hydrogen is. A hydrogen atom, there's one proton in the nucleus, and there's one electron around the outside. Well, if a hydrogen loses its electron, then what does it become? It's just a proton. So when you hear the term proton donor, that is an H+ ion, which is called a hydrogen ion, which is right here. All right, and so what you're going to see is Bronsted-Lowry acid, okay, is going to donate a hydrogen. So if you look in this example here, you have, H and just X, because for any nonmetal, plus water makes H3O plus X minus. So what happened was this donated a hydrogen. So that is my acid. This received or accepted my acid. So that is now a base. Because the definition for a Bronsted-Lowry base is a proton acceptor. All right, so that is going to receive a proton, and this is going to donate a proton. So anything that is a proton donor is a Bronsted-Lowry acid. Anything that is a proton acceptor is a Bronsted-Lowry base. Here's another example, and this is ammonia, okay, plus water is going to make ammonium ion plus hydroxide. All right, well, which of these donates a proton? Well, if you look, NH3 becomes NH4. So it did not donate, it took a proton. So my water in this case is my acid because it donates a proton to NH3 to become NH4. So this is my base because it accepted a proton. All right, and so you're going to see that over and over again. Now, the next term that you're going to see is conjugate acid and conjugate base. Well, what does that mean? A conjugate acid is if you're going the opposite way. That's what the word conjugate means, going the opposite way. So now, if I'm going the opposite way, so now the reaction is going this way, and I have NH4 plus OH minus, which of these is my proton donor? It's going to be NH4. So that is called my conjugate acid because it's a proton donor. My OH minus ion is going to be my proton acceptor. So that's my conjugate base. And so what you're going to see is your base turns into your conjugate acid, and your acid turns into your conjugate base. And the best way to deal with that is go backwards. So if I go backwards here, that's the easiest way to find out what is what. Which of these is going to donate a proton? This one will. So that's my conjugate acid, and this is my conjugate base because it's going to accept an H to look like that. So my acid becomes my conjugate base, and my base became my conjugate acid. All right? So you're going to see that we have hydrogen ions, hydroxide ions, and the other thing is a hydronium ion. Now, in water, what happens here is this H plus is going to mix with H2O, and it's going to become H3O plus. So even though it says H plus, it's actually going to become a hydronium ion, which is H3O plus. So those are going to go hand in hand with that. Now, the other thing I want you to see is, notice in this example, my water was an acid. In this example, my water was a base. If you look at this term here, it's called amphoteric. Amphoteric is a substance that can be an acid or a base, and water is a great example of that. And here's another example. If you have HBr plus water, okay, what is my acid and what is my base? If I have HBr plus H2O makes H3O plus Br minus, which of these is my proton donor? This one is. So that is my acid. Water is my base because it accepts a proton to become like that, like H3O. Now going the other way, what is my conjugate acid? What is my conjugate base? Of these two, if I'm going this direction now, this is going to be my proton donor, so that's my conjugate acid. This is my proton acceptor, that's my conjugate base. Okay, and then there's one final example here, and you can see, you can check it. Did the acid turn into conjugate base? Yes, it did. It went from HBr to Br minus, and then this one went from H2O to H3O plus. So my acid turned into my conjugate base, my base turned into my conjugate acid. My last example here, I have ammonia plus water. This is my base because it accepts an electron. This is my acid because it donates a proton, not an electron, I'm sorry. All right, so the last thing with these is monoprotic, diprotic, and triprotic acids. Okay, a monoprotic, mono means mono-y mono, like one-on-one. That is any acid that has one hydrogen. Okay, so anything like HCl, HBr, those are all monoprotic acids because they have one hydrogen. Diprotic acids would be things like H2S and H2Se. So hydrosulfuric acid and hydroselenic acid, those are diprotic. Now, triprotic acids are going to be things that have three hydrogens, like hydrogen and nitrogen together make H3N. That's hydronitric acid or hydrophosphoric acid. Now the last thing with mono, di, and triprotic is what if it's with a polyatomic ion? Then it's also the same. If I have a polyatomic ion like acetate, which is C2H3O2, it only has a -1 charge, so how many hydrogens do I need? I need 1. So that is a monoprotic acid. Even though it's got all this other junk with it, still monoprotic. If I have hydrogen and then I have NO3, which is nitrate, which is a -1, I still only need 1 hydrogen because it's only a -1 charge. So a diprotic with a polyatomic might be like carbonate because it's a -2 charge, and so I put it there. It's carbonic acid, or sulfate becomes sulfuric acid, and it's a diprotic acid also. And then the last one is, what about a triprotic? I've got phosphate, which becomes phosphoric acid. That has a -3 charge, so I need 3 hydrogens. Or borate becomes boric acid. I need 3 hydrogens. So that is also a triprotic acid. All right, then the last thing would be naming acids. Okay, when we're naming acids, you're going to either have binary acids, which has 2 elements, like this column here. There's only 2 elements involved. When you have that, you always have a hydro prefix, and they always end in ic acid. So it's the root, it's hydro plus the root, and then ic acid. So this would be hydrochloric acid, hydrobromic acid, hydrosulfuric acid, hydroselenic acid, hydronitric acid, and hydrophosphoric acid. Then ternary acid is hydrogen plus a polyatomic ion. You never have hydro prefixes with ternary acids. It's always just whatever the root of the polyatomic is. If it ends in ATE, it becomes ic. If it ends in ITE, it becomes OUS. So this is acetic acid because it comes from acetate. ATE becomes ic, so acetic acid. This is nitrate, so it now becomes nitric acid. If it was HNO2, that comes from nitrite. So nitrite is going to become nitrous acid. So there's no hydro prefix. That's how you know that it's a polyatomic. There's no hydro prefix in the name, or if you're just looking at the formula, you can see that there's more than 2 letters. If there's more than 2 capital letters, then it's a polyatomic, and it comes from that. So we're going to do some practice with that. All right.